Hello! In this video, we present the retrosynthesis of Tegoprazan, a drug belonging to a new class of anti-ulcer medications, the potassium-competitive acid blockers. In this retrosynthesis, a substituted benzimidazole and a chiral substituted cromanol are generated as key precursors, which in turn are prepared from accessible raw materials, as we will see later on. Initially, one of the nitrogen groups of the imidazole ring is protected through a functional group transformation, with a benzyl group to generate precursor 2. The ether group present in 2 acts as a retrone, and based on a Mitsunobu reaction, a carbon-oxygen disconnection is applied, which generates the substituted benzimidazole 3, and the chiral cromanol derivative 4, where the carbon configuration has been inverted with respect to the configuration of that same carbon in precursor 2, and the OR group, corresponding to a good leaving group. The amide group in 3 acts as a retrone, and based on an amidation reaction, a carbon-nitrogen disconnection yields ester 5 and dimethylamine 6 as a raw material. The phenolic ring in 5 has the ketone 7 as a tautomeric isomer. The carbon-carbon bond connecting the carbonyl group in 7 to the imidazole ring is disconnected based on a Friedel-Crafts reaction to open the ring and produce carboxylic acid 8. The double bond conjugated to the ester group in 8 is considered a retrone, and using the Staub's reaction, a carbon double bond disconnection generates aldehyde 9 and succinic monoester 10 as a raw material. The cyclic N-amino group present in the imidazole ring in 9 can be formed by the intramolecular attack of the secondary amine on the aldehyde in 11, which arises through a carbon-nitrogen disconnection in 9. A carbon-nitrogen disconnection of 11, considering a nucleophilic substitution, gives rise to the amidin 12 and bromomalonaldehyde 13. Amidin 12 can be generated by the Pinner-type addition of benzylamine 14 to acetonitrile 15, which arise as raw materials. Bromomalonaldehyde 13 can be generated by bromination of malonaldehyde 16, which in turn can be obtained from diketal 17, which arises as a raw material. The protected cromanol 4, through a functional group transformation, yields cromanol 18. The chiral alcohol in 18 can be obtained by asymmetric hydrogenation of chromane 19. The ring containing the carbonyl group attached to the benzene ring in 4 can be generated through a Friedel-Crafts type cyclization, consisting of the intramolecular aromatic acylation of the carboxylic acid 19. A functional group transformation in 19 generates the primary alcohol 20. The ether group in 20 acts as a retrone, and a carbon-oxygen disconnection based on a Williamson-type reaction yields phenol 21 and chloropropanol 22 as a raw material. The hydroxyl group present in 21 can be incorporated into the benzene ring by substituting the bromine atom in 23, taking advantage of the electron withdrawing effect of the 2 fluorine atoms present on the ring, which facilitate a nucleophilic attack by a hydroxide on the brominated carbon. The introduction of the bromine atom to the benzene ring requires introducing an activating group into the ring that directs to the ortho position, given the position of the 2 fluorine atoms meta to the bromine atom, which direct electrophilic substitutions to the ortho and para positions. The amino group meets these requirements, in addition to being a group that is relatively easy to remove once it is no longer needed. With this idea, a carbon-nitrogen connection generates aniline 24. Next, a carbon-bromine disconnection produces aniline 25, where both the orientation properties of the amino group as well as the properties of the fluorine atoms favor the introduction of the bromine atom at the required position. The amino group in 25 can come from the reduction of the nitro group present in 26, which in turn can be generated from metadifluorobenzene 27, which emerges as a raw material. In summary, here are the main disconnections. The resulting synthesis will be presented in the next video.